Calculating the equilibrium constant K. So, in order to calculate the equilibrium constant K, we'll need to know a few things. One, we'll have to have a balanced chemical reaction, so then we can write the equilibrium constant expression. And two, we'll need to know the concentrations of each of the relevant species at equilibrium. So, for example, let's say we have an equilibrium between butane, which is 4 carbons, and then there's some hydrogens here. There's CH3, CH2, CH2, CH3, and isobutane, which is an isomer of butane. That is a compound that has the same chemical formula but a different arrangement of atoms. So you'll notice that now there's a CH3, CH, CH3, and another CH3 up there. Well, let's say we have an equilibrium between these two. And when we reach equilibrium in an extremely small flask, we have 5 molecules of isobutane, and we only have 2 molecules of butane. What would be the equilibrium constant in this case? So, first we'll write the equilibrium constant expression, K, and that's equal to, remember, products over reactants raised to the stoichiometric factors. Well, there's a 1 here and there's a 1 there. So it is simply the concentration of isobutane divided by the concentration of butane. And in this case, we can just substitute in the numbers because they are equilibrium values. So we'll say we have 5 there, 2. So the equilibrium constant in this case is 2.5. For our second equation, we have the Ka expression for this acid, which is chlorous acid. So HClO2. Now that's aqueous. We have it reacting with water, and that's making chlorite and H3O plus, or H plus in water. And at equilibrium, let's say that we have 0.12 molar of the acid, and then not much of it actually dissociates. It's a weak acid, so we have 0.03633 molar of the corresponding anion and of H plus. So if we want to determine the value of the K for this reaction, first, again, we'll write down the K expression, which in this case is Ka because that's an acid. Remember, products over reactants. So we have here's a product. Another product. And then divided by our reactants. Now again, we don't put water in because it is the solvent, and solvents do not go in the equilibrium constant expression. Then we will simply input in each of these values into the K expression and then simplify. So And if we do that, we should get 1.1 times 10 to the minus 2. Now you may be asking yourself, what are the units of K? And you'll notice that we put in a molarity here, and there, and there. And so if we were to assign a unit to this, you may think, well, there's a molarity divided by another molarity, but there's another one there, so that's in units of molar. Well, actually, we don't assign units to K. We're merely using K as a ratio of products to reactants. And so it is considered to be a unitless quantity. So that's it. No units on the end. All right, we have one more problem that I've prepared. And that is, we have a carbon solid plus carbon dioxide gas in equilibrium to make 2 carbon monoxide gases. And in a 2-liter flask, we've placed 0.1 mole of carbon monoxide, 0.2 mole of CO2, and 0.4 mole of carbon. Actually, that is the concentrate, or that's the quantities at equilibrium. So we should evaluate the equilibrium constant. Now, first, again, let's write the equilibrium constant expression. So we need products over reactants. So there's 2 products here, 2 COs. So CO, and then squared, because there's a 2 here. And then divided by concentration of CO2. And remember, we don't put solids in the expression. So even though we may know that we have 0.4 moles of carbon in the flask at equilibrium, it doesn't matter how much carbon we have at equilibrium, as long as we have some. It's important to have a little bit left. That way, in case it wasn't at equilibrium, we could establish some of that. Because if we ran out of one of the substances, then that would be a little bit not the right thing. So we're going to calculate the concentration of each of these, plug those numbers in, and evaluate the equilibrium constant for this. So if we calculate the concentration, we just need to take the moles, divide it by the liters to get the molarity. So this will be 0.5 molar, and this will be 0.1 molar. All right, because 0.2 divided by 2, 0.1 divided by 2 should be that. And for this one, we don't care because it's a solid, so don't care. So we simply plug these numbers in. And then evaluate this expression. And you should get a K of 0.025. And again, no units on it. So that is how to evaluate what K is, assuming we have all the concentrations at equilibrium.